Hi there, welcome to this lecture series. When an atomic nuclei don't have enough binding energy to hold the nucleus together due to an excess of either protons or neutrons, a radioactive decay occurs, and the nuclei is said to be unstable. In this short video lecture, we will discuss the most common types of radioactive decay, specifically alpha decay, beta decay, and gamma emission. Let's start. This is the outline of this lecture. Let us start by discussing this standard nuclear notation for various species of atom. This is useful in writing nuclear reaction equations. And we have here the element, which refers to the symbol of that specific element. So it can be carbon or let's say hydrogen. So we have H or C. Then A here at the top left part referring to the atomic mass number or the nucleon number. Next, we have Z here shown at the left bottom part, which refers to the atomic number or the number of protons. Last, we have Q, which is the charge. It is 0 if it is not an ion. Next, we have this example of a fission reaction using this notation. And this is popular because this is the uranium-235 fission process, important in a nuclear reactor. Slow neutron is used here with the energy of about 1 electron volt will impact a uranium-235 nucleus, and this will result to a uranium-236 product shown. Uranium-236 is known to be unstable and it oscillates until a fission proceeds. Fission produces fragments of intermediate mass. So for this case, we have the krypton 89 and barium 144. We have also 3 neutrons. For this case, neutrons will be released as well with an average of about 2.4 neutrons. And an energy Q with an average of about 215 mega electron volts. But for this example, we have 177 mega electron volts. Shown above is another fission path for uranium-235. And we have here 2 neutrons and a Q value of about 200 mega electron volts. Isotopes of an element have the same atomic number but different atomic mass number due to different quantities of neutrons. The chemical properties of different isotopes of an element are identical for the case of isotopes, but they will usually have large differences in nuclear stability. Here we have the isotopes for carbon. Using the standard notation we have introduced previously. Note the difference for their atomic mass number A. So we have carbon 12, carbon 13, and carbon 14. Okay, now we extend our discussion of standard nuclear notation in this couple of nuclear reactions. First one is for nitrogen 14 producing oxygen 17 as the product. Your nitrogen 14 will interact with an alpha particle, and this will produce oxygen 17 proton and this Q, a certain amount of energy. This can be written in shorthand form as shown, wherein we have here the alpha that interacts with the nitrogen 14, and we have your proton that is one of the products together with your oxygen 17. Same thing with this second nuclear reaction. Your boron 10 here captures the neutron, producing lithium 7 and helium 4, which is just the alpha particle. The Q here refers to some amount of energy. This is popular, the second equation, in radiation therapy for treating, let's say, a brain tumor using the so-called boron-neutron capture therapy. This is also observed in the reactor, nuclear reactor, control rods. to manage the criticality of a nuclear reactor. Note that boron-10 is known to have a high neutron capture cross-section, or the probability that it will absorb a neutron is high. There are three processes of radioactive decay: the alpha decay, beta decay, and gamma decay. There are other types of radioactive decay modes other than these three, such as electron capture, internal conversion, proton emission, and others. I will make a separate video about those decay modes later. The mass of the reaction products should be less than the mass of the original isotope. We now define here this disintegration energy Q. This is the difference between the rest mass of the original minus the product, as shown in this equation. So first decay is alpha decay. An alpha particle is emitted, and that is just an helium nucleus, so He4. The atomic number is reduced by 2, and the mass number is reduced by 4 when an alpha particle is emitted. Examples are uranium-238 and radium-226, as shown here. First, this equation, uranium-238 decays to thorium-234 with this alpha particle here. So for the radium, we have radium-226 that decays to radon, the daughter, or the progeny, radon-222 plus this helium nuclei. One interesting phenomenon in an alpha particle is quantum tunneling. The nuclear force acts as a square potential well, as shown. So this is the square potential well, the violet graph here. And this traps the alpha particle in the nucleus. In classical physics perspective, it is not possible for an 4 to 10 mega electron volt alpha particle to leave the nucleus with the peak potential barrier of about 30 mega electron volts. However, quantum tunneling allows a finite chance of leaving this barrier. In beta decay, a beta particle, either a fast energetic electron, beta minus, or a beta plus, which is positron, positively charged electron, is emitted from an atomic nucleus, transforming the original parent nuclide into an isobar. And when we say isobar, it means same number of nucleons. So we have the same A here, but different chemical element, as shown here. A neutron transforms into a proton by emitting two particles. It includes an electron and an antineutrino, as shown in this equation. So we have the electron, or a beta minus, then we have an antineutrino. Or conversely, a proton is converted into a neutron by emitting a positron and a neutrino. To satisfy the requirements of conservation of energy and angular momentum in beta decay, it is necessary to postulate a new particle called the neutrino. It has no electric charge and almost no rest mass. Beta decay is a consequence of the weak force. The weak force allows a quark to change its flavor by the emission of a W boson that results in creation of electron antineutrino or positron neutrino pair. Okay, so now let's talk about gamma decay. When a nucleus falls from an excited state to a lower energy state, it may result in gamma emission. It happens mostly after an alpha or beta decay if the nucleus is still in an excited state, indicated by this asterisk shown here. It occurs immediately about 10 to the negative 10 seconds. The energy range of the gamma are commonly about 1 mega electron volts to 1 giga electron volts, which is quite large compared to the X-ray due to the transition of the orbital shell electrons. One example is the beta decay of boron-12 shown here. Your boron-12 will decay to carbon-12 excited state plus these two particles. We have your electron or beta minus plus your antineutrino. This carbon-12 in the excited state will go to a lower state and it will emit a gamma radiation. The reaction energy Q can be defined using this illustration. We have this nucleus X, then bombarded by particle A. It may transmute into another nucleus Y and will release particle B, shown by the conservation of energy, which includes the rest mass energy before and after the nuclear reaction. We can write the following. This refers to the rest mass and kinetic energy of particle A, rest mass and the kinetic energy of nuclei X, and this is equal to the rest mass and kinetic energy of particle B plus the rest mass and the kinetic energy of nuclei Y. By rearranging this equation, we can have the following. The reaction energy Q is defined as the mass difference shown here, or the energy difference. So this is the after the reaction minus the energy before the reaction. Again, this can be written using this shorthand notation shown here. And the Q, the reaction energy as we have defined previously, is positive if the reaction is exothermic, meaning the energy is given off in terms of the kinetic energy of the products or through gamma ray emissions. Q is negative if the reaction is endothermic and the incoming particle must have a minimum energy in order for the reaction to occur. While if Q is equal to 0, this scattering event is said to be elastic and the total kinetic energy does not change. In a nuclear reactions, it is possible to produce an isotope that is radioactive and may decay. Shown here is aluminum-27 bombarded by your alpha particle. It will produce phosphorus-30 plus a neutron. This one is radioactive, and given it is radioactive, it will decay to silicon-30 plus this positive electron here, or positron, plus your neutrino. The production of radioactive tracers is one of the practical use of this induced radioactivity. Radioactivity that is created when stable nuclei are bombarded by ionizing radiation. For example, we have this stable isotope cobalt-59 shown here becomes the radioactive isotope cobalt-60 under neutron bombardment. This is done in an operating nuclear reactor where we expose the sample to the neutron flux. And note that this cobalt-60 here is a gamma emitter which is utilized, let's say, in a radiotherapy facility. Now let us define a nuclear cross-section. A nuclear cross-section is the probability that a given nuclear reaction will happen. And this is the equation. Sigma is your nuclear cross-section, and this is equal to the number of reactions per second per nucleus over the number of projectiles incident per second per area. This is defined as an effective area size of the nucleus for that specific reaction. But please note that we are referring here to the probability. A common use unit for nuclear cross-section is barn. 1 barn is equal to 10 to the negative 28 square meter. Now, if a massive nucleus, for this case, let's say uranium-235 breaks, there will be a net yield of energy due to the mass of the fragments, and it will be less than the uranium mass. We have here the fission paths of uranium-235. A slow neutron will be captured by the uranium-235 nucleus, making it unstable that leads to nuclear fission. The energy release per fission is about 200 mega electron volts, and will be the kinetic energy of the fission fragments. This can induce a fission in other nuclei, creating a chain reaction. So this is how your nuclear reactor works. I will introduce here the reproduction constant K, which is a measure of a self-sustained chain reaction. K is the average number of neutrons from each fission event that will cause another fission event. If your K is equal to 1, the reactor is critical and the reaction can continue steadily. When your K is less than 1, the reaction is subcritical and it will die out. Last, if your K is greater than 1, the reaction is supercritical. When two nuclei join together to form a heavier nucleus, energy is released. The energy released per unit mass is greater than the fission reaction. Well, the challenge here is this. How will you make the two light nuclei close enough together so that the short-range strong nuclear force will combine them together? Here, we have the three-part proton-proton cycle generated by our sun to produce the energy that reaches us. It is a set of nuclear fusion reactions by which stars convert hydrogen into helium. Hi, if you have learned something in this video and you like my content, please consider subscribing my YouTube channel, JP Academia. See you in the next video.